There we go. Okay, so in A2, we're going to be focusing on sequences. And again, in sequences, that means that at this point, we're not adding up the terms yet. We're just considering the terms themselves. So the first thing we're going to, and this will be a little bit related to the question Parjit was asking about a minute ago, is we're going to consider Theorem 8.1. And this is on page 607 for those who are trying to follow along separately. So Theorem 8.1 says, suppose, try to write down some of the key parts of it. Suppose you have a function f of n, which is equal to a sub n for all positive integers n. So again, the notation for that is an upside down a. So this means that you could give the values of a sub n as a formula, like 2 times n or something like that, as an example. But that the function f is a function. Like normally you could write f of x and you could plug in everything you want, anything you want. And in particular, the function agrees with the formula for what you would get for a sub n when you plug in integers. So then it says if the limit as x goes to infinity of the function is some number L, then the limit of the sequence is also L. So this theorem is designed to just help us use tools from when we evaluated limits in chapter 2 or even 4 using L'Hopital's rule to try to evaluate a limiting term of a sequence. Now we were just getting limits of series where we add things up. This is not a series, this is for a sequence. So let's look at an example real quick. So let's say I have a sub n is equal to 1 minus 1 over n. So I'm just making this up, so I'm not referring to a page number because this is not from the book. Find the limit of the sequence of a sub n's if it exists. So we can sort of, as an example, just take a note of what we have here. So I can write that the sequence of a sub n's is equal to, and then I could literally write out terms. So when n is a 1, I get 0. When n is a 2, I get 1/2. When n is a 3, I get 2/3. When n is a 4, 1 minus 1/4 is 3/4. When n is a 5th, 1 minus 1/5 is 4/5. And then I'm going to write dot, dot, dot. So this is just to try to help visualize and understand what the sequence is. I'm sorry, yeah, the sequence is. So the goal is to find the limit of this sequence. So you can imagine that what you're trying to say is the limit as n tends to infinity of 1 minus 1 over n. So this, again, your immediate reaction would be to use the strategies that you had in chapter 2 to try to evaluate this sequence. But this is a little different than a function. But what theorem 8.1 tells us is that since we can let f of x be equal to 1 minus 1 over x, and then we can see that for all whole integer values n, f of n would be the same as the sequence value with that n value. Then this tells us that the limit of the a sub n's is equal to the limit as x goes to infinity of 1 minus 1 over x. So that's, evaluating this is what our natural reaction would be to do when trying to evaluate this. But as we've mentioned before, there's the possibility that these aren't always both doable. So if you have an expression for a sub n involving n, which works fine for all values of n, even if they weren't integer values, like if you consider the function version of that, well, then you can just treat it as if it was just a normal function. But for example, if your expression for a sub n has like -1 to the nth power, or a negative number to the nth power, you cannot apply this theorem, and you could not do this. It doesn't work. In any event, so the purpose for this is to sort of say that we can apply the normal tools of evaluating limits even when we're working with terms of a sequence and we're trying to determine whether the sequence has some limiting value. Okay, so having said that, is this something where we could evaluate this? People feel comfortable evaluating this limit? So you may recall that if we have x going to infinity and becoming very large in the bottom of a fraction, then as the denominator is becoming 100, 1,000, a million, a billion, the overall result of that fraction will be that it goes to 0. And so that in that case, the result of this limit would just leave the 1. So that means since we can just sort of approach this like a normal limit, then we can evaluate the limit of the sequence and get a 1. Questions, comments, discussions about this example?
I have a question, Professor.
Yeah.
So, can you just reiterate how you know when you can't approach it as a regular limit? So here you replaced n with x. When can you not do that?
So you don't actually need to replace n with x. That's not I don't want us to get caught on that formality. The basic idea is if I'm looking at the yellow expression that I've written circled, boxed in blue here, that if you could evaluate that limit as if it was a normal function, then you can use those strategies. That's what this is basically saying. So an example of when we couldn't do that so easily, so let's do this, just for to compare to another example, is let's say I had, well, let's be real, let's say I have a sub n is equal to -2 to the n. So our problem with something like this is that if you consider f of x equal -2 to the x, what do you think about that function?
Yeah, it doesn't look like you can just take a limit as normal.
Well, more importantly, that's just, we've never defined a function that way because it's problematic as whenever n is not a nice whole number, right? So for example, f, this is over the real numbers. I'm not talking about complex numbers. F of 1/2 would be -2 to the 1/2, which is undefined. And that's true with like any like decimal, like, a decimal, a non-whole number input for the x value is going to make this function immediately undefined. And so all of the rules of how we would like to do this and evaluate limits and stuff don't apply to that function, and we just can't use them, which means that we can't use them for the sequence either. I can't take a limit of that as n goes to infinity, for example. Now we could discuss that some other way, but we couldn't use limiting techniques that we had used in chapter 2 because this function, doesn't exist for most values, and therefore all of our limit work from before doesn't apply. Does that make sense at all?
Yeah.
Yeah. Now, it's a theorem that basically says most of the time you can do what you want to do, but we will have cases like this with negative numbers to powers where we're going to have to look at them sort of differently and think about them just as they are in and of themselves without anything from chapter 2. Yeah, so it's a theorem. It's just how they start 8.2, and this is the idea behind it. I don't think you'll effectively make it feel like you're using some special trick in any of the problems or some tool, because it's basically just giving you permission to use tools from the past for most of the problems that we do. All right, so let's consider theorem 8.2, still on the same page. They don't even give an example between the two, as I just provided. So now they're talking about the limit laws for sequences. So back in chapter 2, we did these things called limit laws, and they basically allowed us to evaluate limits of more complicated things more easily by using the distributive property and things like that. And so there's 4 of them here. And it basically says that, well, I don't want to just copy all of this down because it'll just look worse on the screen. So let me look at one of them, and then we'll refer to the others and sort of say how they continue in this vein. So the first one states that the limit as n goes to infinity of a sub n plus or minus b sub n. So we had a limit law back in chapter 2 that said the limit of a sum was the sum of the limits, meaning the limit of f plus g, meaning functions, could be calculated by doing the limit of f plus the limit of g. And this is basically going to say the same thing. So this says that you could evaluate this if you were able to figure out the limit as n tended to infinity of the first sequence. Then you could add or subtract from that the limit, if you could figure it out, as n tends to infinity of the second sequence. Now, when they write out the theorem, in the setup to the theorem, they say, well, let's assume that this is equal to A and that this is equal to B. Then the limit of A sub n plus or minus B sub n would be A plus or minus B. And that's assuming that you could figure out these 2 limits of the individual sequences in the first place. So the 4 properties that were in the limit laws that are then regurgitated in Theorem 8.2 to apply to sequences is that the limit of a sum is the sum of the limits. That's this first one that we just looked at. And then you have the limit. Oh, forgot to change color. The limit of, it used to be a constant times a function, but we're going to do a constant times the terms of a sequence. And again, assuming that the limit as n goes to infinity of a sub n is a, then the limit as n tends to infinity of c times a sub n would be c times a, whatever you get. Basically, this means if you're trying to take the limit of a sequence and there's a constant multiple in there, you can pull it out of the limit when trying to evaluate the sequence, just like you did with limits. And then lastly, 3 and 4 state that the limit of a product of sequences is the product of the limits of those sequences, and the limit of the quotient of two sequences is the quotient of the limits of those sequences, provided that the bottom one doesn't go to 0 when you're dividing. So again, this is a theorem. It's a bunch of juggling notation. So let's look at an example. This is basically going to give them license to have you trying to evaluate the limits of more complicated sequences. So let's look at example 1 on page 608. And they've got a bunch of parts to it, but let's see. Let's try A. Let's keep it simple for now. So it gives us a sequence. A sub n is equal to 3n cubed divided by n cubed plus 1. So the instructions say determine the limits of the following sequences. So that means we want to find the limit as n tends to infinity of a sub n, where a sub n is given here. So what do you guys think about that?
So did we just know that we take the limit to infinity?
Yes, so again, a sequence is a series of numbers. And there's only one place it goes. The terms of the sequence just keep heading off toward infinity, assuming it's an infinite sequence. If it was a finite sequence, then it would have no limit. The only time we use the idea of a limit when applying to a sequence is if the sequence is infinite. And because this isn't a function, we're not going to take a limit as n goes to 5 or something, because n means natural numbers, and natural numbers don't go to 5, they go off to infinity. And that's an example of how we have to separate the ideas we thought of before, where we're taking the limit of a function as opposed to the limit of a sequence. Does that make sense, Parjeet?
Yep, got it.
Yeah. So it's again, we're trying to draw on some of our comfort and experience from the past, but also recognize how we have to treat this a little differently than what we've done in the past.
Professor, I have a quick question.
Yes, please.
Okay, so how do you know that this is an infinite sequence? Because you're not given like any.
Yeah, so if you write a sub n and there's no restrictions on n, then we kind of, best way I can describe it is that you're going to by default assume that n could go to infinity. Why do I have to stop plugging in numbers somewhere? And secondly, and as we were just describing, if we are in the context of discussing a limit of a sequence, well, the definition of a limit is a number where the terms, as you continue on, get infinitely close to that value. And so if you had a finite sequence, you don't continue on. The sequence just has some numbers and then it just stops. And so when we're talking about a limit of a sequence, it will always be an infinite sequence. It doesn't make any sense to talk about the limit of a finite sequence. Does that help?
Yes, yes, it does. Thank you.
Yeah, again, it's just wrapping our mind around the new type of problem we're dealing with, the notation, the terminology, and we're trying to pull in ideas from chapter 2 about limits to focus specifically on the idea of the limit of an infinite sequence. Okay, so how about looking at this expression for a sub n, 3n cubed over n cubed plus 1. Could we evaluate that limit? What do you guys think? Questions, comments, discussions?
Would it just be 3?
It would. And so we can't plug something in, right? So we have to sort of try to draw back on our ideas of how to evaluate a limit. And I think that for many students, that's very stale or forgotten or feels funny applying in this context. So Cielo, are you able to help us understand why you think that's a 3?
Oh, I mean, I kind of just do L'Hopital's because if you plug infinity, you would just get infinity over infinity.
Mm-hmm.
So that's in the indeterminate form. So you could just take the derivatives of the top and bottom separately.
Very good. Did you actually take those derivatives?
I could do it right now.
No. I'm just asking you if you were mentally able to come up with the 3. Your justification is completely correct. So I'm not trying to like force you to do extra work or anything. I'm trying to help people understand the logic behind it, because there's actually 2 ways to look at this limit. And one of the ways is they would have done this in chapter 2 before L'Hopital's rule was even introduced. But you're absolutely right that L'Hopital's rule could be applied to this as well. I don't think that usually shows up until chapter 4, chapter 3 or 4, later on. So there was 2 ways to think about this. So the first thing is that we could imagine ignoring the 3, because in the limit laws that we just looked at, one of them is that you can pull out a constant. So let's say I just played with this right on the screen here a little bit. So this constant, you can imagine just ignoring it. Or you could think of it that we're going to take 3 times the limit as n tends to infinity of n cubed over n cubed plus 1. Let's see. Infinity over infinity equals 1 or indeterminate? Is that a question from Marcus? Yeah, that's indeterminate because it depends on how the infinities were arrived at. But when it's indeterminate, then you can use L'Hopital's rule to see if you end up with a 1. For example, while we're looking at this case, if the power on the n in the top was a 4th power and the bottom stayed the same as it was, we would still have infinity over infinity, but that would no longer simplify to 1. All of a sudden, that would be infinite. Or if I reverse that, if the top stayed as a 3rd power on the n and the bottom was n to the 4th plus 1, I still have infinity over infinity because they're both going to infinity. But now, because the bottom is of a higher power, the entire ratio, instead of going 1, would go to 0. If they're the same powers, we can say it's a 1. And here's an example of how we could observe that sort of algebraically. So that's why I was saying, if you were in chapter 2, the conclusion that you just drew is something we'd like to support instead of trying to memorize to try to make sense out of it. And here's the way that that's usually shown. So let's say I take this away. So the way this is usually shown algebraically is that you can imagine multiplying this by, or basically dividing the top and the bottom by whatever the highest power is. This is the algebraic simplification that's usually used to try to help make sense of the fact that this is true, what you just said was true. So if I multiply the top and the bottom by that, I'd end up getting Well, in the top, let's see if I can color coordinate this. In the top, these would cancel out because n cubed times 1 over n cubed is 1. And in the bottom, I would distribute the 1 over n cubed to each of those terms. And so what I end up with after I do that simplification is that I get a 3 in the top since those canceled out. And then in the bottom, n cubed times 1 over n cubed is 1. And 1 times 1 over n cubed is 1 over n cubed. So if I multiply, or the way they'll describe it as dividing the top and the bottom of the fraction by n cubed to divide out by the highest power, algebraically, the ratio we started with is equivalent to this thing on the right. It's the equivalent to this. And since I'm taking the limit as n goes to infinity, then this part here, the only part left with an n in it, would go to 0. And therefore, we can conclude that the whole thing settles on the 3. Questions or comments about that? So the challenge here is that some of these limits, you may have some sense of how to evaluate. Maybe you'll go to L'Hopital's rule if it applies. That's always a possibility. Maybe you'll just kind of remember if the powers are the same, you get a 1, and if not, I have to do something different. But at some point, we're going to want to try to justify these a little better, because as they get more complicated, you end up just getting lost. It ends up being like you just don't know what to do unless you have some way to apply something to the problem and simplify it into something that's easier to evaluate. That makes sense. And I think I just ran out of time.